thank you. Thank you for this kind introduction and for the invitation to give this talk. So today I will talk about MSxplain. But first, before we enter into the new project that we are about to start, I wanted to give you some background of all the developments we did before arriving at this point. We conclude, of course, with the future work. So let me first talk about machine learning for magnetic resonance imaging in the assessment of multiple sclerosis. I have to start with just one slide to introduce multiple sclerosis for those that are not familiar with such illness. Is an autoimmune inflammatory disease of the central nervous system. And it is a disease that is degenerative. So you can have a diagnosis early when you are young, and it will go in a degenerative manner with some cognitive and physical decline over the years. There is no curation for such a disease. It has a quite impact over the worldwide population, with up to about 3 million, I would say. I'm going a little bit 2.8 millions. And it is having a higher prevalence in countries with a higher income, like Switzerland. There are biomarkers that help us in the diagnosis and in the prognosis of this disease, like, for instance, this NFL protein that you can extract from the cerebrospinal fluid. And there is as well biomarkers that are driven by imaging. And here is where the MRI, the magnetic resonance imaging, comes into the picture. So for those that are not familiar with MRI, this is a non-invasive imaging technique that will give you a 3D view of your body in vivo. Here you see one of the brain, where you can depict the lesions. And there is conventional modalities that you can extract from an MRI scanner, and there are other that are more advanced. And I will come back to this a little bit later on. So MRI in MS is super important. It's really used in a clinical routine with what we call conventional or clinical type of MRI sequences. You see here some examples on the right. And it is mostly historically used to find out white matter lesions that are appearing in multiple sclerosis in the brain and the spinal cord. And it has been used in terms of finding what are those lesions and looking at the changes of those lesions over time. This is really a biomarker that is included in the criteria for evaluation of MS, the clinical criteria. This is very interesting from the machine learning perspective. And as it was presented before in the talk of the speech processing, we addressed this with classical techniques in the past, by doing our feature extraction and then applying our KNN or SVN algorithm. And now deep learning is here to stay. And this is not updated. And there is a lot of works appearing in that sense. So what we can do new about it. In my group, we have been rather more focused in exploring other aspects of MS. One of them exploiting these advanced sequences that are not maybe so widely used in clinics, but they are very interesting for a better diagnosis and prognosis of the patient. And we have been as well exploring via generative models some problems like the partial volume. This is a problem that occurs in any digitized image when you have smaller structures, and in the same voxel or pixel of your image, you have several structures appearing. This is very relevant when you are looking for these teeny things in the middle of the brain. But what I will talk today about is the cortical lesions. So I will talk you first on these advanced biomarkers and why they are relevant. And I will start with these cortical lesions. So in the cortical lesions are very important, and they have been only very recently introduced in the clinical diagnostic criteria for MS. And they are very interesting because they appear already at the very early stages. They are present in all the types of different phenotypes that MS has. And they actually better correlated with the clinical and with the clinical symptoms, the cognitive and the physical symptoms that the patients have. This is the degenerative scale that I was referring before. So for this reason, they are really relevant, but they are not really so explored in terms of machine learning or deep learning. First, because they were introduced recently, and there is a lack of really widely data sets imaging those lesions. They are very tricky. They are different than white matter lesions because they have different intensities, and the intensities that they present are kind of very mixed with the gray matter intensity of the brain. They have less prevalence, so you have less samples. From a machine learning technique, we know that this is very tricky. And the context where they appear is much more difficult. They are not in the middle of a white matter of an homogeneous region. They are at the interface. But we took the challenge, and we have been exploring how to tackle these cortical lesions in the past. And this is the work of my PhD student, Francesco La Rosa. And we did that in a way that we tried to put it as much as possible in the minimum input setting, just using two modalities. One that is clinically acquired, and the other that is more advanced, but still feasible in a very short time. We went to the minimum to capture the most smallest lesions that we might imagine, 3 voxels in our images. And we took a classic, I will not enter it into details, but it's a classical UNet architecture. We call it UNet minus because we were indeed simplifying the architecture, reducing layers. And we did that without any pre-processing. And it appears that we were really doing quite a good job and in a cross-validation, but as well in a pure testing and multicentric study. We are as well extending this not only to the classical clinical scanners, but as well to the ultra-high field scanners. These are scanners that are quite rare, I would say, but very interesting from the clinical perspective to understand the disease. So our scanners at 7 Tesla. And we as well take into account the same type of architecture. We were doing some input dropout strategies to be robust to some of the modalities that were having artifacts. And we increased the complexity because we were trying not only to say this is a cortical lesion, but as well which type of cortical lesion it is. But I've been telling you that I wanted to go to a minimal setting and ideally to a setting that could be used in clinical practice, right? But I've told you that I've been using an image that is not so clinically acquired. And this image is the MP2H. So one of the problems that we have been facing is, okay, but since in practice, I don't have this image, how can I apply your algorithm to detect the cortical lesions if it's not acquired? So we have been as well exploring image synthesis problems where from clinically acquired images, like the MP rate that you see here on your left, that is commonly acquired in the clinical MS protocols, we are synthesizing this advanced imaging that we like so much, that is the MP2H. So MP2H is special because it has a reduced shadow bias field that often occurs in this type of images, and it has a very good tissue lesion contrast. We approach this with GANs, and basically the contribution of this approach was to leverage different losses. I would not enter again into the details, but it is to have losses at the voxel level, at the feature level, and at the image level. And we were combining these to create this MP2H. Our study was evaluating the ability of this synthetic MP2H in the case where there was not an MP2H acquired. And we compare then its usage with the other flag that you saw before, and as well comparing with the real one acquired, the synthetic MP2H. Overall, the message is that we were not able to detect more lesions with the synthetic MP2H than with the original one. And this is good than with MP2H because we don't want a synthetic image to invent new lesions. But it helped improving significantly the delineation voxel-wise and the volume estimation of the lesions that are as well important biomarkers. The last biomarker, advanced one that I wanted to present today is the paramagnetic rim. So paramagnetic rims is a ring that you will see around the lesion. And this is an important feature because it has been correlated with a more chronic disease. And the people that present more lesions with such a feature are actually having a more aggressive disease. Just let me show you a little bit what I'm talking about. So here you see an image where there are different contrasts. To imagine the rims, we have to use other type of advanced sequences. And what you see here, it's that maybe can convince you that you can see a lesion here with a black hole around. I think it's quite obvious. And here you basically do not see much. Here you see the same lesion image with the flare, that is the classical clinical sequence. And then in the bottom, you see two other lesions. It is less obvious to decide if this is a rim or not. You see partially some of this effect, but not completely. And here you see something like looks like a rim. But just to tell you that on the left, even if it was not complete, it is a rim. And on the right, even if it looked like a rim, it is not. So this is a very, very advanced biomarker from the clinical perspective that is very relevant, but there has quite of a high inter-rate of disagreement yet. But we took the challenge to try to train an algorithm that took these patches around the lesions and learned to distinguish the features or the lesions that were having this rim appearance or not. And overall, we were as well exploring from which image modality we could do that. So we were benchmarking all the different image modalities. And interesting, with only one acquisition, this T2 star, I wouldn't enter into the details, but this is only one single image that you extract from the MRI. You can actually have a very good performance in taking this decision. We were doing this as well in trying to use the power of the MP2 rates that maybe you understood. This is a modality that we like a lot. And we like it a lot because it can be the bridge to translate what we are exploring at 3 Tesla. 3 Tesla is the clinical scanners with the 7 Tesla, the more research-oriented. And we are still struggling with several aspects. This algorithm, it works around patches. So you have to identify first the lesion, and the lesion has to be kind of alone. And in MS, we have often confluent lesions, so several lesions that in turn has been fusioned together, and this creates some problems. But still, we are working now on doing this. Okay, so this is just to present you very in a nutshell all the different image analysis techniques, to talk to you about the MRI, the advanced biomarkers that are interesting. I wanted at this point just to thank the people that has been contributing, because this is a work with MR physics, with of course doctors and many people. But then how I am arriving at MSxplain, which is the problem of this? So the problem is that we have these advanced biomarkers, the cortical lesions and the rims, that are very, very interesting from a clinical perspective. And let me then first introduce you Christian Meyer. He's an engineer, 45 years old, and he was diagnosed with MS. And then suddenly, so he's experiencing less ability to concentrate in work and maybe a lack of coordination while skiing. So he goes to his neurologist with these symptoms. The neurologist will do MRI to try to see which is the activity of the disease. But the clinical sequences are not so specific to be able to find this activity. So that the treating neurologist knows that there is a center while they do this advanced MRI that I've been talking to you about. The MP2 rates, the T2 star, the phase. And this researcher knows people like us that we are able to process AI-based techniques to analyze those advanced biomarkers. So these new sequences will help, are more specific, to find out these cortical lesions and rims. The decision of the treating neurologist is very complicated. From the conventional MRI, it doesn't really know if it has to change the medication or not. There might be a medication that helps, but without knowing which is the real activity of the disease to the subject, it is not easy to assign that medication, because it comes as well with secondary effects. So you will not give a medication if you don't know if that person will be more or less responsive. With the new advanced techniques and the new models, we could better answer this question, and importantly, that the treating neurology can better more substantiate that such an important decision. And it's a decision that will come very often in the progress of a disease of an MS person. So it's really a difficult decision. So we have all the pieces a little bit in there, but there is a lack of flow. There is really not this feedback from the AI models towards the treating neurologist, or importantly, towards the patient. So this is a lack of integration that we want to address in MSxplain. And the other is as well to evaluate or to give more trust for the neurologist in order to take such a decision. So this was really to give you a real practical case example. So our goal is really with MSxplain, what we are trying to do is to assess if really we can use this trustworthy behavior of deep learning algorithm, in our context is in neuroimaging, to support the prognosis in multiple sclerosis. And we have three objectives at three different levels. First, engineers, medical doctors, and patients. So we really think that with such an approach, we will be able to improve the models on one side, of course, to increase the quality of the decision of the doctors, just as the example I explained you. And ultimately, ideally, what we want is really to help as well in a better understanding of the disease, of the inflammation and degeneration of this disease. So to achieve these objectives, we split the project into 4 aims. The explainability, to really have a better insight on the models. The interpretability, so can we really make this link on the decisions with meaningful concepts and biomarkers for the doctors. To give as well an idea on uncertainty, how secure we are when we are changing of our domain of the input images, for instance, and to feedback as well this uncertainty to explainability and interpretability. Sorry. And ultimately, of course, most importantly, I would say, in my opinion, the integration part, because we really have to put these tools into the environment where physicians work in an everyday practice. So I'm very honored to present for the first time the team. I think it's the first time I'm presenting this slide. So the Hassler Foundation was financing this project, and we are very enthusiastic about it. They financed 2 PhD positions and 1 part-time software engineer. As you see, I think one of the strongest points as well is that we have this interdisciplinary, and we complete on the expertise on the different teams here in Sierre, in Basel, and of course as well in Lausanne. So remember, cortical lesions, I will refer sometimes to model 1, and paramagnetic dreams, I will refer to model 2. From a machine learning perspective, one is a simple voxel-wise segmentation, the other is a classification problem. So the first aim is the explainability, and this is something that is quite well known, and that we would like to use more as a sanity check. Our idea is really to use the classical silencing maps that we can compute with quite a state-of-the-art techniques to see which are the areas of the image that have been used to take the decisions. This is more, as I'm telling you, as a sanity check, and it can help us in just identifying some bias. But we are very aware as well of the limitations that such techniques have. We have some strategies to mitigate the different instability, I would say, of those explanations, but I think they are a first step that needs to be done. The second is more important in healthcare, and it's really more than exploring these silencing maps, those perturbations at the voxel level. We really want to understand the perturbation at the biomarker level. And this is something that it's really crucial in healthcare. And here it comes the idea of regression concept vector. So I was inspired by the pioneer work of Mara, and we would like to translate the same type of approach. So we have first to define which are the concepts that can be quantified, that are clinically relevant. And then we have as well the possibility to link through the attribution, the regression at different points of our architecture of the layer weights with the decision being taken, and regress this with the concepts defined. So at the very end, if you want, you have a little bit winning concepts, so I can say, that would give you which is the concept that a perturbation will change more the decision of your network. And this is not a one shot, this is something that it has to be built iteratively, and I think it can be very, very valuable. From a methodological point of view, these regression concepts were more based on a classification model, and for a voxel-wise approach, we will need to do further analysis, but I think it is very interesting. And what we are expecting from such an approach is that we can really, on one side, linked to the clinical degenerative impairment, the EDSS scale, or the protein measurements I was telling you, and as well, sorry, what it is very relevant in this case is the histopathology, I would say, where this is the unique ground truth that we have in MS, and it could be a good way as well to link with this rim lesion of inflammation and use such a type of information together. The third aim is more about uncertainty, and we really believe that providing this information to the doctor, it can really help the visual assessment that they do on the images. I will not enter into detail about how we will be able to compute the uncertainty, but just to recall you that what we want to do is to link back the uncertainty of the model and of the data to the other two types of explainability. And this is the only work that we start, because the project only sorry, I forgot to say the project only started 1 month ago officially. So this is why I'm presenting you more what we want to do than what we did in the past. And it was very nice because we started with aim 3, so we didn't start by the beginning. Okay, but it was very interesting, a new collaboration that Mara brought together with Batsal Raina and Professor Gales and Dr. Malini, I don't know how to pronounce it, sorry, where we were trying really to formalize this uncertainty study for MS. We started with a simplified version on really only flare images, very clinical, only white matter lesions, but they did an impressive work. And our idea is really to be able now to explore this domain shift about different sequences because of different clinical centers, different patients, different scanners, different annotations. And this is really very relevant. And you see here the first results. I thank Vatsal for giving this animation, where he's plotting the 3D flare, what it would be a manual notation of a doctor, what it would be the AI decision, and how this decision is uncertain in which areas. And we are waiting to know if the challenge submitted and NeurIPS will be accepted. And last but definitely not least, it is this integration part that I'm telling you this is very important. It will be based on the pioneer work of Professor de Pensange, where they, Quantimetry, sorry. So there is an ongoing, already quite advanced project where they were putting in place already this type of solution. So basically you have a part that is managed, the KOPS platform that can manage very well the data set on one side, and then anonymization, and on the other side you have more the web interface when you could, this is a schematic scheme where you could really provide such a measures and give as well an easy access to each of the users to evaluate the tools. So we want to really to integrate some of the measures I was just presenting you, and to be importantly to have this experience feedback, and there are talks about this today later on, very interesting, an expert feedback on how these explainability tools might help and in which context. We understand here that it was very difficult to expect that really experts will be able to take the time to work with us, but we were thinking that it would be equally even most relevant to have junior researchers, and this could go in a more educational usage of the tool. So overall, I wanted really to present this idea of explainable AI, that it was already important before in the classical machine learning techniques, but at least before I was more sure about what I was providing or what my supervector machine was using to take a decision. And now it's really quite dangerous, I would say, in my opinion. This is very in line with the Swiss MS cohort and the Swiss MS registry that are now ongoing in Switzerland, and in I think as well in a good complementary aspect for the SPHN project. So to conclude, and we already saw this morning. I thank the speakers because this is just my thoughts on AI and healthcare challenges, but you saw these challenges are shared as well for the speech and in many other applications. Medical imaging is complex because of the nature of the images, because they are huge and they are multimodal, and because we don't have cats and dogs, right? So the number of samples is very low. We saw as well the talk where we had this issue on the annotation. So for medical images, again, it's not a cat or a dog, it's much difficult to annotate. And we have strategies to mitigate this, like the weak labels from the reports. We have this generability, that this is something ongoing since 20 years ago at least, when I started. And what I think is now more relevant is this interpretability. So I still think, though, that we should be able to leverage what we know and prior knowledge on medical imaging and each application, that is a lot, and our experience. And the two more challenging things are still this domain translation, domain shift, and the integration. And yes, this is the publicity moment when I'm saying that there is an open position for a postdoc. if you like what we do, you can contact me. And with apps. No, well, the most important, I would like to thank my team, and not only those working on MS, but all of them. It's really great. They really do a great job. And you for your attention.